So now, if you look at the graph, there is the initial position. Let's say you are on top of a building, which is 96 feet tall, okay? And you are throwing something. You're throwing something upwards. And obviously it will have an initial velocity, as I said. Since you're throwing it um, uh, in any direction, let's say to upwards, that's easier to visualize. And if you throw anything upwards, as I have tried to show, you can clearly imagine it will reach its maximum height after a certain time, right? It will not keep going. Do you agree? It will keep going for a certain time, then it will stop for a fraction of a second, and then it will uh, start coming down again. That means it will gain its maximum height at some point. Do you agree to this discussion? It's really important. You can actually visualize it. You can actually try it yourself. Okay, just throw something upward. You'll see it will reach a point, and then it will start coming down. At that point where it stops for a fraction of a second and then starts coming down, it's the point we say that it has gained its maximum height. Do you agree? Anyone?
Yes.
Isn't it interesting? Because you can actually visualize it. I found it, when I was a student, I found it really interesting because I can actually see what's going on, or I can actually, do it myself, this experiment to visualize it. That's really interesting. And I'd recommend you guys to do the same. Okay. All right. So that's the first thing I wanted to tell. The second thing is when the particle or whatever you threw upward, when it reaches its maximum height, it stops for a second, right? As I said, because then it comes down, it starts coming down. So at the maximum height, the velocity is 0. Do you agree? Can you visualize it? Don't just agree with me. Just try to understand what's going on. Okay. When it reaches the maximum point, that means, in other words, if I say when it starts coming down from a certain height, do you agree? Just before that, it actually stopped for a fraction of a second. It's difficult how long it was stopped there. We can still calculate it mathematically if we know all the other informations, but we're not really concerned about it. Do you agree that it actually stops at the highest point, at the maximum height? Is there anyone who is still confused what's going on, or why does it stop there? Or I would say, uh, how do you recognize, or how do you see that it actually stopped there?
It's at the same point where velocity is 0.
Uh, same point for what?
Velocity equals 0.
No, velocity is 0, but I didn't understand your question.
Oh, it wasn't a question. I was just, yeah, never mind.
So my question was, at the highest point, at the maximum height, the velocity becomes 0 for a while, for a fraction of a second. Do you agree with that? Is there anyone who is still confused? Because you'll need this concept, and I don't want you to memorize it. even without understanding that it actually becomes zero. Okay, now if we agree that it becomes zero for a while, now what if I say it? All right, so first of all, I did mention the last time that velocity is a vector, right? That means it depends on the direction it's going. That means, in other words, if I try to reiterate it, if if we throw it upwards and if we say it's the positive velocity, when it will start coming down, we'll say the velocity is now negative. That means since it has changed its direction to the exact opposite way, then whichever we initially said is positive, the opposite direction will signify uh, the velocity as negative. I think we said it the last time as well. Um, Let me show it for, yeah, this is the problem where you said it, right? If the car is traveling to the east and we say the velocity is positive, then whenever it starts going to the west, I mean the opposite direction, we say the velocity is now negative. So whenever you see a negative sign, it doesn't mean that you are doing it wrong. It actually means it's the velocity is working towards the opposite direction, nothing else. Okay, so when you threw the ball upwards, the velocity was positive because as we are defining it as positive, generally we define the upward direction or the right hand direction as positive, and obviously negative for the opposite direction. Okay, so when you threw it, the velocity was positive until it becomes zero. It became zero, right? And then it stopped for a while. That's why we're saying the velocity is zero. And then it started coming down again, right? That means the particle is moving to the opposite direction. The direction we actually sent it to, it started coming down in the opposite direction. And that's why you can see after it became zero, the velocity is actually negative. Can you see that? The velocity after it reached the maximum point, maximum height. Obviously, at that point, velocity is zero. But afterwards, you can see the velocity is negative. It's below the x-axis. Can you imagine it? Take your time, okay? Don't just agree with me. Try to imagine why is that? Why it's happening, okay? No question at all? Okay, that means you agree with what I'm saying. Okay, so if that's the case, um, Let me see if I can give you a problem to work on. No, I think I have to generate one. So let us do it this way. Uh, I'll generate one problem in the break, the 5 minutes break, and then I'll give you after the break, okay? Now let's just continue the discussion, okay? All right. So this problem was about um, the initial position and the velocity. I mean, if you throw something upwards, um, then it reaches its maximum point, it stops for a while. At that point, the velocity is zero. Then it starts coming downwards and the velocity becomes negative. This is the idea. You will be uh, needing, you'll need um, for some future reference, okay? Okay, now let's see what else can we do with these graphs. So um, if you're given a graph, and from this graph you'll be let's say you are asked that uh, can you find the value, let's say at 2010, I guess, yeah, it's 2010. This t-axis is the year after 2000. So this is the year 2010. So the question might ask you, hey, can you find the number of internet users, obviously in millions, uh, in the year 2010? So this will be a straightforward question. You can actually eyeball it from the graph. You can go straight up from the year 2010 and see where it's taking you. And then you just need to go to the other axis. So let's go to our left. And if you start going to our left, we can see it's 2000. That means in the year 2010, there were 2000 millions of internet users. So this will be a really, really short question. You might see a question like this. It will not be the entire question though. You'll have several other parts where you can use this graph to find some other informations. Okay. And it might tell you uh, to find the instantaneous rate of change, or I would say the average rate of change. Yeah, I think the average rate of change would be a good question. We have already seen that, right? We have already seen how to do that. So let's say I'm saying that, hey, find the average rate of change from the year 2012 to 2014. So what should you do? We just need to see the end point at 2014. We are here at 3,000 million. And at 2012, we are here at 2,500 millions, right? So we just subtract the initial value from the end value, and we divide it by the change here. So this way we can calculate the average change, right? Average rate of change. So this can be another part of the question, right? Okay, let's see what we have next. Okay, growth rate. All right, so this can be another question. So this is the years, let's say after 2000. It doesn't need to be after 2000 all the time though, so that you just don't get confused. It can be any time span, any time duration. And it's the growth rate of something, let's say the number of uh, people in Laramie, the growth rate in Laramie, okay, since the year 2020, or rather 2000. And what this means that, from this graph, you can actually see how does it work. So at, or rather on the year 2000, this is the year 2000, right? you can see it's slightly below this 100 mark, slightly below. It's not exactly on that 100 mark. That means, let's say it's 99 million per year. That means in that year, 2000, the growth rate was 99 million. Okay. And we can actually do that for any other years to find the growth rate from this graph. These are pretty obvious questions, but again, it will have several other parts. And I'll generate one question in the break, and I'll give you so that you can work in groups, okay? And it will make more sense then. Okay, let's see another graph. Okay, so this graph shows the number of items on the x-axis and the cost in dollars in the y-axis. And this graph is actually this function for this function. This is the cost function. We say it as the cost function. And this is the straight line, which will give us the cost for the number of items. And now you might be wondering, what can we get from this function? Even if we are not given this function, we can actually, not given this graph, we can actually calculate the initial cost for this particular item. Because we can see this function is in the form of y equals mx plus b, right? This is the m, x plus b. And we know b is the y-intercept. That means when x is 0, this is going to be our value for y. So that means for this function, even if we don't have any item, that means x is 0, we still have $500 to pay. That might be the initial investment. That might be the utility bill for the warehouse. This could be anything, but this is something you will always need even if you don't sell or even if you don't have any number of items. So this way you can see we can derive information even from the function, right? Okay. Let us see this definition first and then we'll go to that. Okay. As I said, that c of x was the cost function. So this cost function gives the cost to produce the first x items in a manufacturing process. So if you're producing something, it will definitely cost you money. So this c of x, whatever that equals to, is going to give us how much will it cost us. Obviously, it will have some initial cost, as I said, like this one. It will have some initial cost. And as I said, it could be, if you are producing it in a place, you need to rent that place or you need to buy that place. There will be utility bills and all that. So this is just the initial cost. And this X signifies how many of those items you're producing. And depending on that X, your cost will increase, right? If you produce more items, it will cost you more. So that's why it says the cost function gives us the cost to produce the first X items. Okay. Now, what's the average cost? Okay. So the average cost to produce those X items will be the total cost over the total number of items. And it's actually the same thing we have been doing for finding average, right? For finding average, we always add the number of things we have, and rather the add the number of things we get, and we divide it the total number of items it needed we needed for it, right? For example, I think I mentioned it the last time as well, and it's a good example, so I can actually use it now as well. So um, if you get 5 out of 10 in the first exam, and if you get 7 out of 10 in the second exam, what would be the average uh, score in the exam for you? So you just need to add those two and divide it by the total number. So you got 5 in the first and 7 in the second exam. So in total, you got 12. And the total number on offer was 10 plus 10, 20. So if you divide 12 by 20, you get 6 by 10. That means on an average, you get 6. That means for every 10, you get 6. You get 60% score. And this is the same thing here as well. We're trying to find the average cost. So we divide the total cost by the total number of items. That's it. Okay. Okay. And the marginal cost, what's that? So the marginal cost is actually the first derivative of the cost function. And what does it give us? It gives us the approximate cost to produce one additional item after producing X items. That means if you are trying to produce one more item, let's say you have already produced X number of items. Now you're trying to produce one more item of the same kind, ideally. Then how much will it cost you? The marginal cost will give you that. Okay, let's see examples of it. Okay, let's try this one. So this is the cost function. And this will be given, no worries. You will not be asked to find this cost function. Okay, you will be not required to find this cost function. This will be either given or obviously at least the function will be given. Okay, no worries with the function. So this means, as you can see, if I try to produce X number of items, this will be the cost for that. So for example, if I just produce one item, let's say just one item, okay? Let's see how much will it cost us. So we'll just plug in X in 1 in place of this X's, okay? Nothing else. It's just the algebra. So if we plug in 1 in place of this, we'll get a negative 0.02 plus a 50 plus 100. So 150 minus 0.02, so it's 149.98. So that means if you just try to produce one single item of this kind, whatever it is, it will cost you $149.98. That means almost $150 for one single item. And we can actually find the cost for any number of items with this function. We can just plug in the value and the corresponding result will give us the cost, right? Let's see the average cost. Okay, so we know to find the average cost, we just need to divide the total cost, which is this, by the number of items. Here the number of items is definitely X. So if we divide it by X, this will have one less X since we are dividing it by X. This X will get cancelled with that X which we are dividing it by. And here we'll have our X in the denominator. This is it, you can see. This is actually derived from this cost function. Again, if the cost function is given, it's not difficult to find the average cost. You just need to divide it by the number of items. And if you divide it by X, you get this function, right? Okay, and again, don't worry. I'll not say, I'll not give you this function. I'll say, hey, draw this graph for me. It will not be asked, or vice versa. I'll not give you this graph and say, find the function for it. Instead, I might give you this cost function and say, hey, calculate the average cost. That means you just need to divide it by the number of items. Okay. All right. And again, from this graph, I might ask you that find the average cost for 50 items. What do you need to do? You just plug in 50 in place of this X and calculate it. Okay. And let's see the marginal cost. As I said, marginal cost is the first derivative of the cost function. Okay. And we already know how to find derivatives of this format, right? So can you do it for me without looking at the solution? Anyone? And you need to explain how to do
It
it.
should be negative, what, negative 0.04x plus 50.
And how did you get that?
Yeah, plus 50.
Yeah, how did you get that? Let's
Using
try
the,
one by one. How did you do this part? Negative 0.02 times x squared.
Using the I guess the power rule.
Power rule, okay.
I did it for both. You have 50 times x to the first. So you move that one to the front, subtract, so that basically goes away.
You can actually remember it for a shortcut. If you have x, the single x, I mean x to the 1, the derivative will always, in the derivative, the x will always get perished. There will be no x.
Yeah.
Yeah. And this part is a constant, right? So we know the derivative of any single constant. That means if nothing is assigned to it, then only the solo constant will become 0. So this part will become 0. This will become 50 since we have only x to the 1. So the derivative of this will be only 50. And for this part, n is 2 here. So 2 will come down and we'll have 1 minus, 1 less exponent here. So it will become x to the 2 minus 1. So it will become x. 2 times 0.02 becomes 0.04. And this is the first derivative. Again, I'll give you the cost function. I might give you the cost function and say, calculate the marginal cost for me. Okay. I may not write C prime of X for you. You need to remember that marginal cost is actually C prime X. That means the first derivative. Okay. And it actually goes on the same way. Okay, so this is another graph, and we have nothing new here for this graph, so we can go for the next one. So the next definition is elasticity. What's that? So in physics, elasticity is the property of a particular, whatever it is, a particular particle or a particular object, which keeps the shape of that object uh, really firm. That is defined as elasticity. If someone is from the physics, I think you have seen it, and obviously you know the better definition, right? What does elasticity mean here? So let's do this. Okay. Let's say we define the demand function, and we say that the demand function will be f of p, where p is the price. Obviously, the demand for a product varies with the price, right? If the price drops, I guess, or I would say, if, in other words, I think I should say, if the demand is high, you will see the price for a product generally gets increased, right? I'm not an economist anyway, but I think you have already seen this somewhere. Whenever you are looking for a product which has a really high demand, you'll see the price is slightly higher than before. A very good example would be the price of the airline tickets. So if you go to if you are trying to reserve a ticket during the Christmas, you will see the price is significantly higher than it generally is in the other months. Have you seen that? Anyone?
Yeah.
I have seen this. I've seen this in all the last 3 Christmas I've spent here. So whenever the demand is higher, you'll see the price is higher. So you can actually denote the demand function with this price associated with this price, I would say, because it actually varies with the price, right? Okay, now we define the elasticity of demand as this. That means the derivative of the demand function in terms of the price. So this dd, small d and capital D, means it's the derivative of this bigger D, or the demand function, and this dp in the denominator signifies it's the derivative in terms of the price p, the derivative of the demand function in terms of the price p, and we multiply the ratio of the price over demand. You just need to remember this. We define it this way, elasticity. Okay. Now, how does it work? Okay. All right. So if you have a demand function, and if the price and the demand is given, I'll ask you to find the price of the price elasticity of the demand. Okay. I'll not give you the graph because it's too complicated, and I don't want you to go over this because it's a smallish semester. So I'd avoid this question. Okay, so that's the good news for you. But what I want you guys to do, it's just all about algebra here. No real calculus here. If it was a core part of calculus, I would have discussed it, but it's actually algebra. Someone is in the waiting room now. Anyway, so I can give you this demand and price, and I might ask you to find the price elasticity of it. Okay, so don't spend too much time on this. You can ignore this. Okay. This is just algebra. So I don't want you guys to spend time on this. Rather, we'll try to spend time on the calculus part. Okay. But yeah, I can give you the function and say find the price elasticity, because you can use the concept of derivatives here, right? You'll need to find the derivative of the demand function. Okay. Okay, now what I want to do is give you a very good example and create a couple of groups so that you can work on groups, for this type of problems. I'll definitely have questions like this in the homework and in the exam. So now I'll take a couple of minutes of break, ideally 5 minutes. I might need a couple of minutes more, but yeah, I'll try to come back within 5 minutes with a question, and then I'll create a group like last time, and I'll tell you to work on groups or in groups to solve this type of problems. Okay, so I'll see you in a couple of minutes. So since this is the position function, we know if we can find the first derivative, we'll get the velocity function for this, right? So all we need now is to do some calculus here. We need to find the derivative of this function, which will give us the velocity function. So 5t squared, 5 is a constant, we can keep it outside by the constant function rule, right? And for t squared, if we do the power rule, we know for t squared we'll get 2 times t to the power 2 minus 1, right? Which is 2t. So 5 times 2t will give us 10t. Do you agree? I'm just talking about this first term. Let's do it step by step. Do you agree? Sorry.
Okay.
And then for the second term, 3t, again, 3 is a constant. We can keep it outside using the constant function law. And for t, the derivative will be 1, right? I think I have told you the shortcut a couple of minutes back that when it's just the linear one, that means the exponent is 1, it's a linear function, a linear term, I would say, then the derivative will just be whatever the constant assigned to it. I mean, the variable will get perished because the exponent is 1. So when you do 1 minus 1, it becomes 0. And for any variable or anything to the power 0, it becomes 1. So it will be 3. So the velocity function will be 10t minus 3. Do you agree? If you are not getting it, please let me know. I'll try to reconvince you. But don't just leave it here, okay? If you don't understand it now, then in future, maybe in the homework problems or even in the exam, you'll be in serious trouble. These are really basic and easy concept, but still tricky. So if you're not getting it for some reasons, don't get demoralized and don't hesitate either. All right, so we now know the velocity function, which is 10t minus 3. The next question was to calculate the velocity of that particular object at t equals 1. What should we do? Anyone who didn't answer in the chat, can you tell me what should you do to find the velocity at t equals 1?
You would then put 1 in place of t, and then times 1 by 10, and then minus 3, right?
Yeah, exactly. So since we want to find the velocity, we just use the velocity function, which is 10t minus 3, and plug in t equals 1 there. So if we plug in t equals 1 there, 10 times 1 minus 3 gives us 7. That means the velocity at t equals 1 is 7. Let me see if we have the unit. Do you have the unit? Yeah, it's measured in feet and second. Time is measured in seconds, and distance or the displacement is measured in feet. Excuse me. So the velocity will be 7 feet per second. Okay, now the most important part of it, if there is any, the acceleration of the object at t equals 1. Now what should you do? Again, anyone who couldn't answer in the chat box, if you could try for me, that would be nice. What should we do? We're trying to find the acceleration of that particular object, whatever it is, at a certain time. What's the first thing we need to do? Okay, anyone? Anyone from the participants list?
To find the acceleration, you're going to take the derivative of the velocity.
Very good. So to find the acceleration, the first thing we need to do, we don't care what the time is, at which time, at which value of t we're trying to find the value of it. The very first thing we need to do is to find the acceleration function itself. And to do that, we need to find the first derivative of the velocity function. Do you agree? We have seen this the last time, I guess in the slide 3.5, or even, I guess maybe in 3.6. I'm not. Maybe, yeah. But yeah, definitely not today. We have seen it the last time. So acceleration is nothing but the first derivative of the velocity function, or you might say the second derivative of the position function, whichever you feel, whichever you can remember, or you feel that it's right. But yeah, you need to remember, I guess you need to remember both, because I might give you a question with the velocity function. I might not give you the position function. So if you just remember that the acceleration is the second derivative of position function, then you might be in trouble, because I might give you the velocity function to start with. So you also need to remember it's also the first derivative of the velocity function. Okay, you need to remember both. All right, so now we need to find the first derivative of velocity function. Velocity function was 10t minus 3. What should be the derivative of 10t minus 3?
10.
So let me do it for you. Excuse me. Okay, so okay, you can see the chat. So for 10t, we can keep 10 outside, and for t we have a power 1, so it becomes 1 times t to the power 1 minus 1, right? And it's basically, I should add a negative. For -3, it's a constant, so it should be 0, right? So it becomes 10 times t to the 0, right? And t to the 0 is 1, so it's 10. See the chat. just use the power rule for the 10t part, and for this 3, we know it's a constant, so the derivative of it is 0. So the acceleration function a of t is actually 10. Now, since the acceleration, we know the acceleration function, now we can find the acceleration for a certain value of t, right? So if I want to find the acceleration at t equals 1, what does it give us?
10.
And why?
Just how it worked, I guess. Sorry.
So the funny thing is, it's a constant function, right?
Yes.
So it doesn't matter what t is, it will always be 10. Can you see that? Because there is no place to plug in the value of t. It's a constant function. So whatever I give you for t for this function, I mean, if I say what's acceleration at t equals 5, it's still 10. It's nothing else other than 10. It's a constant function. Do you see that? Just take a look at the chat. I have written it for you. And let me know if you have any question. No questions at all? All right. Let's end this and go back to the slides. Okay. All right. So we'll start the new slide 3.7, and it's the mighty chain rule. We'll need this, as I said, probably the most times, along with the product rule. Okay. So let's start. This is the chain rule. Okay, don't get stressed by seeing this. Okay, let's first see the definition, and then I'll show you examples of it. So the chain rule is basically telling you that if you have more than one variables, or I might say more than one functions in a single function, if you have more than one variables, or if you have a composite function, that means more than one functions to calculate, then what should you do to find the derivative? So for this one, for this type of functions, we actually subdivide into the functions, into the different functions we have. Okay. So let's say we have a function y equals f of u. Let me start sharing my screen from my iPad. So I want you guys to have this slide open, okay? Please have this slide open. Now I'm going to share the screen. So it's 8, 6, 8, 21. And for this function, for y equals f of u, we want to find the derivative, okay, where y itself is a function, u itself is a function g of x. So we want to find the derivative of y in terms of x, where y is a function of u and u is itself a function of x. If that's the case, we want to see how to do that. So now, again, we are trying to find the derivative of y, in terms of x, right? That's dy dx for you. Now, since y is a function of u, we can actually find the derivative of that in terms of u. And since u is a function of x, we can find the derivative of u in terms of x and then multiply it. Even though you can't really cancel this, because it's the derivative, it's not really something separate. There is no separate du here. You can't really do this. You can't really cancel these two. But still, just for making sense, you can see if we cancel these two, what does it leave us with? It leaves us with dy dx. That's the exact same thing, right? So we can do this modification, but again, don't do it, never ever, because it's not, you can't do it, because it's not the ratio of these two, by the way. Let me tell you why. This is basically dx of y. That means you are trying to find the derivative. Sorry, I think it should be u. Sorry about that. That means you are trying to find the derivative of y in terms of u. And for the other part, it's basically ddx of u. That means you're trying to find the derivative of u in terms of x. So that's why you can't really cancel like this. I mean, obviously, if you cancel this, you get this in return, which makes sense, but it's not exactly working like that, okay? So the chain rule is this. Whenever you have a function in between another function, you just subdivide it into those functions you have. I know it's looking kind of awkward or bizarre, but let me show you one example of it, okay? And hopefully it will make more sense. Let me take one example. Let me start with a really easy one. Let's say we are trying to find the derivative of y equals sine, let's say e to the u, okay? No, I think, yeah, I think we can do that. Sine of e to the u. And for this, I'll use, no, I think let's leave it for the second part of the theorem. This is the first part of the theorem. Let me show the second part first, okay? Then you can go for it. Okay, yeah. All right, the second part of the theorem says, if you have a function in between another function, that means a composite function like this. Oops, have I used more? No, I think I have done a good job. Okay. If that's the case, the way to find the derivative of this type of function, this type of composite functions, is find the derivative of the first function, okay, and then multiply it by the derivative of the second function. So the derivative of the first function is this, f prime, and the derivative of the second function, g prime. Okay, so this example is we are going to use the second part of the theorem, okay, and then I'll pick another function for the first one. Okay, so we are trying to find dy dx, right? So what should we do? Dy du, I would say, yeah, not x. Dy du, and it's a composite function. Can you see that? Right? What should we do? So we need to find the derivative of the first function, which is the sine.
So mo ti sọ fún ọ pé ẹ kúkú tètè lọ sọ ẹ sọ fún ọ Sunday àbí ẹ tètè lọ sọ fún ọ báyìí pé ẹ rí cash gbà o tí wọ́n ní ẹni ọdọọdọ lọ ní
Lope,
cash
are you trying to say something?
wọ́n lè mọ̀ so tó bá di latest time
Lope?
20 yẹn.
I don't know why do they do this every time. Anyway, let's go back to the discussion. So the derivative of the sine function, that's the first thing we need to do. There you can see the derivative of the first function, right? What's the derivative of sine function? Anyone? What's the derivative of sine something, whatever it is?
Is it the negative cosine of that?
Almost, not right, but almost.
It's positive
Positive.
cosine.
Positive cosine, very good. So cosine of e to the u. Okay, whatever you have here, doesn't matter. The derivative of sine will be cosine of that. Okay, positive, yeah. And then the second part, you need to multiply the derivative of the second function. That means which is inside, or you might say for the composite function, which is the g function for you. What's the g function here? It's e to the u. What's the derivative of e to the something? Let's say e to the uw yo. What's the derivative of that? Anyone?
Isn't it like UYOE to the UYO power?
So we know the derivative of e to the x is e to the x. So the derivative of e to the u, since we are doing it in terms of u, is e to the u. So the derivative of this in terms of uwyo is this thing itself. So this means whatever you have as the exponent of e, I mean as the exponential function, excuse me, if you are doing it for the same variable, I mean if you're finding the derivative for the same variable like this, then the derivative will be the same. there will be no change. But if you're doing it with a coefficient, oh, sorry, it should be u. If you are doing it with a coefficient, this m, that means if you have anything other than the variable, then this coefficient will come down and you'll keep the rest. Okay. So this is the use of chain rule. This is the answer. This is the final answer. What we have done here, let us recap everything. So if you have a composite function, by the way, it's the example of the second part of the theorem. I'll show example of the first part as well. We'll do a lot of problems from the chain rule. I'm planning to do at least a whole session for it. Okay, so if you have a composite function like this, the first thing you need to do is to find the derivative of the first part of the function. So here we have sine and exponential. That means it's a composite function. So the first part of the function is sine, the sine function. We know the derivative of that is the cosine function. So this is the f prime of gx. On this occasion, it's u though, f prime of gu, doesn't matter as long as you remember how to do it. If the variable changes, no worries with that. I can give any variable. It doesn't need to be x all the time, right? Okay, so it becomes cosine of e to the power u, or the exponential function of u, right? And then you need to find the derivative of the function inside. That means this g of x, or on this equation, it's g of u. So the derivative of e to the u in terms of u is always going to be e to the u. It will never change, right? So this g prime of x is g prime of u on this occasion is e to the u. Again, you need to remember this format. Don't just memorize it, because I can always change this x to u or y. I wouldn't give y, but I can change it to u, v, or t, s, anything. You just need to remember how to do it. So whenever you have a composite function, find the derivative of the first part and then multiply the derivative of the second part. Okay. Let me show one more example, and then I'll give one example to you so that you can practice. Okay, let's try. Again, all of these are for the second part. We haven't seen the example for the first part as yet. Okay, so let's try another example. Let's say y equals e to the sine x. Let's just change the order. Okay, now what should we do? What should we do? We're looking for the derivative of y equals e to the sine x in terms of x. That means we're looking for dy dx. What should we do? Again, it's a composite function. That's the first thing. Do you agree? If I say it's a composite function, do you agree?
Yes. Well, the first thing you should do is just separate out into the two functions, right? So it's e to some piece that you're going to derive,
Right.
and then you're also going to do sine of the x, which you're going to derive.
Very good. Exactly. So let's just forget what we have here. Okay. The first thing is to find the derivative of the e function. Okay. So what's the derivative of e function? We know whatever we have, if we don't have any other coefficients with it, no worries. So we can actually copy this here, e to the sine x. That's the derivative of e, right? But we're not yet done. The next thing is the part we ignored. That means the function inside the function, which is sin x. We need to multiply the derivative of that here. What's the derivative of sin x? We know the derivative of sin x is cosine x. And this is our answer. So again, for the derivative of a composite function like this, you just find the derivative of the first part, doesn't matter what you have inside, and then multiply the derivative of that part which was inside, which you ignored in the first place. Any question from this? Take your time. I have told you before, and I'm repeating now, that this is really tricky, and there is only I wouldn't say only, there is a small or really small margin for error. Okay, it's really easy to get carried away. It's really easy to make a mistake. But if you know what's going on, if you practice 10 or 15 problems and do it properly, then you will see that this is fun. This is really fun to work with. Take your time, okay? See if you have any question. Any question from these two problems? Let me show it together. Yeah. From these two problems, let's look at this derivatives and see if you have any question. So both the problems you can see is a one-liner. That means we can actually find the derivative in one line. But you can see we are doing a lot of things in that one line. Even though it's just a one-liner problem, as I said, you don't need 2-3 lines or even 2 lines for it. Forget about 3. You can solve it in one single line, but you can see there are so many things we're doing here. If you don't have any question, I'll give you a problem and I'll give you time to work on it, okay? Do you want me to give you the problems? No opinions? Okay, I can see one thumbs up. Okay.
Yes, you can give us.
Okay, so this is your problem number 1. Y equals, again, find the derivative all the time for these problems, okay? Okay. So let's say y equals sin x, and 2, I'd give you okay, try this too. And again, I'll create a breakout room for you. Again, we have 17 people out there. So that means one of the groups will have 5 people. Anyway, let me create the breakout room. And then we'll work in groups, okay? All right, I'm creating the group and I'll see you in, I think you should not need more than 5 minutes for it. Yeah, let's see you in 5 minutes, okay? And if you have any question, write it in the chat. Okay, here you go. Okay, we are back. So, the first question would be, were you able to do these two problems? Is there any group who couldn't do any of these problems? At least from your concept, you could do it wrong, but at least could you try and maybe reach a better conclusion which looks good to you? Okay, so let's just solve it now, okay, without wasting any more time, because we have 5 more minutes. I want to solve it before we wrap it up today. So let's try the first one. Dy dx would be, so first of all, we want to find the derivative of tangent function. What's the derivative of tangent function? Anyone?
Secant squared x.
Secant squared, not really secant squared x, secant squared whatever we have, right? Secant was squared this. Okay. Then we want to find the derivative of, okay, let me use this color. For this, we want to find the derivative of e function. What's the derivative of e function?
Is it
It's-
cosine e to the sine x?
The derivative of e function is the e function itself. And then we have another one to calculate here. We have actually 3 functions, okay, not 2. It can be done for any number of functions. So now we want to find the derivative of sine x. And the derivative of sine x is cosine x. Yeah, I know you have told the answer together, but I want you to do it. I wanted to do it separately so that it makes sense. How can I use the chain rule? And this is your answer. Okay, so for the tangent function, oh, sorry, we have found the derivative of that. The derivative of any tangent function is the secant squared of that, right? Then in between we can see the e function. For this e function, we know the derivative will be the same, whatever we have. And then we have another function which we can use in this chain procedure, which is the sine function. The sine function, the derivative of it is cosine x. Now, how many of you did it properly? How many of you have got the same result? You can give me a thumbs up. If you haven't, no worries. It's the very first time you're doing it. So no worries, we can practice a lot more. So only one of you got it right. I can see only one thumbs up. Still no worries, because it was complicated because I had 3 functions instead of 2, right? The problem I showed had 2 functions, e and sine, e function and sine function. But here we have tan function, and I mean tangent function, e function and sine function, 3 functions here, right? So if you haven't get it right, if you haven't got it right, no worries. Now let's try the other function and see how does it go. Again, we have 3 parts. First of all, sorry about that. I was supposed to write E here. Gosh, sorry. Sorry about that. My bad. I apologize for it. I was supposed to write E because you can't have x to the power something and use the same procedure. For that, you have a separate rule. We'll see that as well. But since we haven't seen that, we can't really use that. I was actually planning to write an E. Anyway, let's do it now. No problem. And again, I apologize for it. So the first function is e function. What should you do? We just copy it here. So if we have an e function, we just copy that here, right? Sine e to the x. Next, we have the sine function. What's the derivative of sine function? It's the cosine, right? So times its cosine e to the x. Do you agree? And last but not the least, we have the e function. And the derivative of e function is e to the x. And this is your answer. I apologize for that x, but any question from this part with the e here? Any question from this derivative? Anyone? Any question? All right. So
Oh, sorry, I was gonna ask a question.
yeah, sure, yeah.
So whenever so say in this case we had e sine e to the sine e of x. So whenever we're doing a derivative, we pull it out. So it's left in the top right there on e sine to the e of x, but we pull it out and put it not in a power format. We just have it multiplied along with the base variables there, right?
For e function, yeah, you don't
Okay.
you don't use it as a power function. Yeah. Any other questions?